Next, now that we know how to calculate the potential due to a point charge, I would like now to be able to compute the potential for any charge distribution. And for that, of course, we're going to use the principle of superposition. We already had a principle of superposition for voltages, so this is just a slightly modified version of superposition for electric potentials. And I'm basically going to use what we already know about superposition for voltages. You will recall that if I want the total, I want the total potential, total electric potential at some location x. And I know that that is defined as the total voltage as I move some charge to location x from my reference point. But that total potential we had previously shown can be written as the sum of potentials from different components of the charge distribution. So that would be the voltage, going from the reference point to x, plus V2, going to x from my reference point, etc. But finally, we know that each of these terms is just the electric potential from the first charge or from the second charge and so forth. So we see then that we can get the total potential, V tot, here, right, by simply adding up the potentials from each of the individual contributions. V1 of x, that's what this first term is giving me. And then V2 of x would be the potential from the second charge distribution measured or computed at location x from the second component. That would give me this one, and so forth. So if I want the total potential at any location in space, all that I have to do is add up the potentials from each of the individual contributions. And since I do know actually the answer for the point charge, this sum then becomes a straightforward exercise if I want to use superposition down at the individual point charge level. So let me give then a final formula for that. So this means, therefore, that if we want to calculate the potential, the total potential at any location x, what we would do is, if we imagine a situation then where I've got point, Q1, charge Q1, a charge Q2, a charge Q3, and maybe there's some location x out here where I want the total potential, what I need to do is to determine these distances. This distance here is R1. This distance here would be R2. This distance here would be R3. And I might have a very large number of these charges. So let's call this last charge Qn. These here are just some dots to indicate an arbitrary number. And I would need then distance here Rn. So the total potential then is going to be the sum over all of my charges n in my system of the potential from each individual charge. And that potential, we've already determined up here, is Coulomb's constant times the nth charge divided by the distance to the nth charge. Now that's a very nice handy formula, because notice now this is actually a lot easier than computing electric fields. To compute an electric field, remember we have this r hat over r squared, or we have to go to the Cartesian. We can either use that trig form, or we can go to the Cartesian form where I have to do vector subtractions. All of that is gone now. Things are much simpler because potential, it turns out, is just simply a scalar. So this is going to be a much easier calculation than the electric field. In a moment, though, I'll show you some nice uses for this potential, and one of those uses makes it very easy actually now to compute electric fields. So this is, though, what it would look like if I had a series of discrete charges. What if I have the continuous case? Well, for the continuous case, it's going to be very similar to how we've handled things before, right? Suppose I have some continuous charge distribution. Let me slide things down here a little bit to take a look at something more continuous. Maybe my situation might involve, I don't know, some kind of curved sheet here. I'll try to sketch some kind of two-dimensional surface. Who knows here exactly what it looks like. And maybe I want to know the potential at some location out here, x. And we all know what the basic strategy is going to be, right? I'm going to turn this summation up here into some kind of an integral. I'm going to divide my surface up into a series of little area patches, maybe, where each patch has a has a little charge on it, dq sub n, right? So I'll have a large number of these patches, and so I will be saying that the potential at location x is going to be the sum over n. Following my formula up here, it's going to be Coulomb's constant times whatever the little charge is, dqn, divided by the distance to that charge, r sub n. Pretty much so far just the formula that I've given to you up here. The magic then comes in is that we can turn this directly into an integral. This then would be the summation goes over in the infinite limit to an integral. Then I have Coulomb's constant on top. I have the little bits of charge, dq, which become then my integration variable, divided by the distance to the corresponding points. And the value of dq then, as you know, will depend on what type of system I'm talking about. For dq, I would have a variety of options. If I have a linear system, right, if I just have like a line, that's going to be charge per unit length times some length dl. Or dq might be some charge per unit area, as in the example I'm giving you here, times the area element dA. Or it might be some solid little chunk of charge and some solid volume of charge, which would have a charge density rho coulombs per cubic meter. That would then have to be multiplied by dV. So we have this then general result here for the continuous case as well.